Right. So let's continue and talk about these trial states. So basically these trial states you can construct from two approaches. Either you construct states that are very well suited to the structure of your problem, or you construct states that are easy to construct with the hardware that you actually have. Usually these two are not the same, unfortunately. So you choose some ansatz that is either problem specific or hardware efficient. So let's say if you have a certain structure for a problem, you think the wave functions will look a certain way, or so you might have an idea of how the state should look, but it might be that to construct this state you need complicated long gate sequences that you really can't implement on your hardware. So let me say a few words about both, with some example from quantum chemistry. So, in quantum chemistry, a common ansatz is called the UCC, unitary coupled cluster. Basically, this is trying to use the structure of that fermionic Hamiltonian that we saw before for the molecular systems in the second quantization picture. So here the trial state psi of theta is given by some unitary operation that is parameterized by theta on some initial state. And this unitary operation is written on the form of some exponential t of theta minus t dagger of theta. And this initial state is perhaps some sort of crude guess. You can get in quantum chemistry often talk about the Slater determinant. So it is basically constructing a fermionic wave function from single particle wave function. So that's some sort of zeroth order guess that you can have. Okay, so what is this T then? That is what's called this cluster operator. Hence the name. And it's a sum of operators indexed by K, where the first one is a sum where where index I is for occupied orbitals, and J is for unoccupied or inoccupied orbitals. And then you have some parameter here, theta, I, J. And then this T2 and you have some I and J. This is a higher order. And you have some parameter in all these indices. So it's something on the form that we saw before that the Hamiltonian have. Now, you can go to higher orders too, but these sort of rapidly decrease in size, so you can truncate. And you sometimes talk about UCC-SD, and that's singlet and doublet. I think that's up to second order here. And then if it's SDT, it's up to the third order. Here the number of parameters, you don't need to say that. So if you go to higher orders, the number of parameters naturally increases rapidly. But since the higher orders also taper off in size quickly, it's fine to truncate.
But you have like theta, there's quite many of those, right?
Quite many of which?
Of these theta parameters.
Oh yes, already a second order. And okay, so this is sort of, we can see this as sort of a similar structure to the Hamiltonian that we were looking at. But how do you implement this in your hardware for your qubits? Because remember, these need to be mapped to qubit operators in some non-trivial mapping, and the actual gates and so on that you need to do for that in that formulation in your actual hardware might be complicated, or will be complicated. So what people instead have done is try what's called hardware efficient and one example is paper from IBM group, Kandala et al. That was in Nature. 2 years ago, where they calculated ground state energies for a few small molecules. So they looked at hydrogen, lithium hydride, and beryllium hydride. And it took like 2, 4, and 6 qubits for these respective calculations. So how did they do it? Well, they start from the simplest initial state you can imagine. Everything, every qubit in its ground state. And then they construct the trial state by applying a number of unitary operations. Some single qubit operations, some entangling operations, and so on. on this initial state. And this, you're repeating this entangling and single qubit operations d times. But each of these steps has its own parameters, so it's not the same entangling operation here as here. So each, let's see, or well, you can use the same entangling operator, but you have this different single qubit rotations each step at least. So they are parameterized by some theta 1, some theta 2, and up to theta d plus 1. So this U single is just arbitrary rotations of each of the qubits. And then you have some entangling gate. And you just take what you have available. You take your best entangling gate for your hardware.
When you say a single is an arbitrary single qubit rotation, there's actually 3 angles.
Exactly.
Okay.
So this in this theta 1, that's in itself a vector or parameter. So you have 3 angles. Yes.
So the idea is just create some weird arbitrary state. You don't care what it is necessarily. You just need to create something that
Yes.
has no structure to it, really.
Yeah, there is, like here you have a structure that was fairly inspired by the problem solving. Here it's just
throw the wall.
Yeah, let's try what we can do and what we can do easily with our hardware. So hopefully, since we are updating parameters and iteratively optimizing anyway, hopefully this will converge onto something that's a good approximation of some more physically motivated initial state. So yeah, you mentioned, so there's 3 angles sort of in each single, and then you have n qubits, so you have like n times 3d plus 2 independent angles in total. So there's quite a lot of parameters.
But compared to the UCC, it's quite few, right?
Let's see. Is it so? The number of orbitals was the number of qubits, so that's n.
But then there's ij there, so n is n squared,
Yes.
right?
Yes.
But then the other one is like n to the 4, or
Yes.
so it's scale.
Yeah.
Is D some?
D is the number of step repetitions. So you start out doing some single qubit rotation, and then you interleave entangling single qubit, entangling single qubit, and the number of times you do that is.
Is it dependent on the phasing times of it?
Yes, so I was just going to get to that actually. So D will be limited by the decoherence. Because it takes time to run, to do each step on the computer, and you want the final state to be some actual quantum state, not some decohered classical state. So you need to stop while you still have something quantum, and that means your decoherence time will limit the number of steps you can do. And that's quite a severe limitation already with these small molecules from today's devices, as I understand it. Maybe Morten can confirm, but I think, like for, at least for this beryllium hydride, they would actually have needed quite a few more repetition steps D to reach this really good accuracy than what they could do because of the decoherence.
I don't remember how many, but there's a couple of them.
Yeah. I think they could only do 2 or 3 repetitions.
I have heard through the grapevine that they have done H2O now as well,
Okay.
and they haven't published it.
But then it's one thing to do it, and another thing to do it sort of to some certain accuracy.
Yeah, they just remove orbitals until they can do it, kind of. So it's a question whether they did it or not.
And also, like, yeah, you remove orbitals to lower the number of qubits you need, but then even if you have a lower number of qubits, you still need a certain number of repetitions to actually be able to converge on the really the right state.
And how many orbitals does one have? Is it number of valence electrons? Or?
Depends. Usually you include the last shell you have, so the open shell. Kind of.
And is it always better to have more number of repetitions?
If you're not limited by decoherence, then if you can do more repetitions, then you can sort of search a larger space, I would say. You can find more, construct more advanced trial states.
I will just make a small comment. In 2018, there was a paper by some people in Google which showed that once you construct these ansatz, you have to have this kind of gradient step where you update your theta by finding the
Yeah, we're
gradient.
getting to the up.
But they showed that as you make the number of qubits more, this gradient vanishes completely. So
For
then,
hardware efficient, right?
huh?
For hardware efficient.
For this ansatz, basically, if you have this ansatz where you apply single qubit rotation and tangling and repeat, you increase qubits and then basically your algorithm is useless because you have these.
Yeah, I also heard that there's like there's probably a cutoff where it's better to use the couple clustered ansatz or the physically inspired ansatz instead of these hardware efficient ones.
So one thing that people are looking at, I mean, all of this is research being done at the moment going on and in the past, just the past few years. One thing that people are looking at now for these NISC devices, when you're really limited by decoherence, is if you can do some error mitigation. And one rough idea, error mitigation is that so you have some certain level of noise that's introducing decoherence in your system. You can't get rid of this noise, sort of, not yet at least. But what you can do is introduce more noise. And then you run the experiment again with more noise, like you get a few data points with increasing levels of noise, and then you extrapolate to zero noise. And it actually works sometimes, so you can improve things with such noise.
So how do they model this extrapolation? Did they just assume all their noise has a particular form and then they just extract back from there? Or how do they?
I want to
Parameter
get
free.
I want to look closer at that someday, but I don't have more detailed knowledge. This is the hand waving. So you can see, actually you can see here that this is quite similar to how you did in the QA, right? You had this, in QA you had the cost Hamiltonian, the mixing Hamiltonian applied in some sequence like this, and you repeated, well, I think you said P times for the QA. So here you see that QA is sort of a subset of the VQE. Yes?
I'm not an expert in QA, but do you have your Hamiltonian in the circuit encoded in QA?
Yeah, one of your unitaries is your cost Hamiltonian.
Yeah.
Because here you have your Hamiltonian outside kind of.
Yeah, then your Hamiltonian has certain form and QA, I guess. But It's you're creating a trial state by applying unitaries, and one of those unitaries is the cost Hamiltonian, and the other is a mixing Hamiltonian. So it's just one way to create the trial state, very obliquely. Okay, let's finish with a few words on how to actually do the optimization. How to update the parameters. Now that we've prepared the trial state and we measure on this trial state and we get some answer, and then we need to decide on what parameters to try next. So maybe you can say first, what are some problems now that we want to find the next set of theta? One thing can be that there are some local minima in this optimization landscape that you're searching through. So you want some method that doesn't get stuck there. Another problem could be that, well, we did these measurements of the different operators and we sum it up to get the energy of the Hamiltonian. But this is just some sampling that we did, right? We measured this a number of times to get some average, and there is some error bar there in what was actually the value of these, the expectation value of these operators, so there's some uncertainty in the energy of the measure. So we have limited sampling. So we only have access to noisy values of energy. So ideally our optimization method has to have some robustness to this noise. Okay, and then I don't think there is a consensus on like what method should you use. Probably it will be different for the type of problem you're trying to solve. I mean the most naive thing you can do is just to do some simple grid search. So you just try out a bunch of parameters, a bunch of different theta in a parameter space, equally spaced somehow, and then you update from there. Or you can do some gradient descent.
But we don't know the gradients in general, right?
No.
So you have to.
So more common is to do some derivative-free. Methods. There are several. One example is Melder-Mead. And then I guess there are I mean, in here you can some Bayesian methods also. And I would say this is also an area of active research. How do you do this step in the best way? I know several of the people in the audience actually have been working on this in different contexts. So I can't do more than give an overview so that this is an open problem. One thing then finally to just think about the practicalities of implementing this algorithm. So there are a lot of things, there are a lot of steps here, and you have to think about things like how fast is it to measure these operators that you need to measure on the quantum computer. How many samples do you take to get the accuracy that you need to be able to make an informed decision on how to update your parameters. There can be a trade-off there also in to actually update your parameters in your hardware, like to prepare that new trial state, can also take some time. It's not just to say, okay, now I have this new theta and magically I get the new state, but you actually need to program your quantum computer to do all these unitaries now with new parameters, and that means new pulse shapes that you need to send down to your gates qubits, and there are a lot of practical details like that that you need to take into account when you calculate sort of how efficient or fast is this method. Yeah.
So this measuring of the operators, you said that the operator that we measure is these Polish strings?
Yes.
Does that essentially mean that we need to do tomography to actually run the algorithm in general? X, Y, Z type?
It depends on the Hamiltonian,
Okay.
I guess. You would like it to be as local as possible, because measuring like 3 local or 4 local terms quickly becomes cumbersome. Then I guess it depends on your exact problem, whether you need to be able to measure all sort of sigma x1, sigma z2 correlators, what exactly you need to measure.
I mean, answer is like you only need to measure the terms that are in your Polish strings.
Yes.
So if your Polish string contains all the terms, okay, then it's full state tomography. But hopefully your problem shouldn't contain all different ones.
No.
So I guess how does the number of measurements you need change based on the number of orbitals you have?
I guess that is not straightforward for me to answer, because that also depends on what mapping are you using to go from your fermionic Hamiltonian to your qubit operators. So yeah, that's not immediately obvious.
I'm just wondering, does it scale exponentially? Does it scale polynomially? What's the number of measurements?
The number of measurements that you would need. Scaling with the number of orbitals.
Yeah.
I think it's n to the 4.
And 4.
At least, yeah.
Okay.
It's with each one, essentially.
That's not the exponential, at least.
Also not the nicest polynomial.
No, but there is also definitely a debate regarding I mean, the WACQT can be applied to many types of problems, but it's most discussed for quantum chemistry. And there's certainly a debate there for how well it scales. I mean, you can do it now for these very small molecules, but these are molecules you can already handle classically, and you can get much better accuracy classically. And then the question is now, well, when we scale up to 100 or 1,000 qubits, will we be able to tackle some molecule that classical methods struggle with? And my impression is that it's still not clear how well it scales. This method, because there are so many steps there that you need to look at the details for. I don't know if you have things to add.
No, I think one of the big problems right now is also how the optimization space looks like when we scale it up. Because that could be really hard to just go in the right direction, I guess.
Yeah. So this was what Chalmers was mentioning also, I guess. Like you can have an optimization space where you have some barren plateaus, where it's hard to find. There's no gradient anywhere.
I mean, it's the same problem, like now instead of getting stuck in the energy space, you get stuck in the parameter space.
So especially for this coupled cluster, if the number of data parameters goes with n to the 4, so if you have 100 qubits, I mean that means you have 10 million parameters optimized.
Yeah. And you have,
well, I mean, no, this data parameters, at least there are.
Yeah. So yeah, I can finish. Maybe I can give you the reference to this review. So. This was a review that I found useful for preparing this lecture. It's on the archive 1710-01. And it's published last year. There was a special issue in a journal called Quantum Science and Technology, where they asked people, what would you do if you had 1,000 qubits? And they were in this review. They discussed the WACQT and how it could be applied to quantum chemistry, but also to other optimization problems. But they sort of dodged the question, I think, of would you be able to, could they really do something useful with 1,000 qubits for this? Any other questions? No, more.
Just a comment, I saw on IBM, they have created this textbook for quantum computers, and then they have this, so going from WACQT, you can do like general linear systems solving as well. So they have this variational quantum linear solver, where you basically just solve linear systems with WACQT.
Yeah, since
in parallel to QAA and WACQT and regular.
It's yet another, I mean, it's all variational
Yeah, exactly.
algorithms.